Hey there, honors biology students. These are notes on water and solutions. Before we talk about water and solutions, we need to review a couple of things. The first one is the polarity of water. So last time we talked about ionic and covalent bonds and that atoms can be bonded together in those two ways. And the two types of covalent bonds were polar and nonpolar. We discussed that an example of a nonpolar covalent bond would be like methane, because it has no charges on the outside of the molecule because the electrons are shared equally among carbon and hydrogen here. So among the two elements that are bonded together, the electrons kind of make a little circle 8. And so electrons are negatively charged, but since they spend equal amounts of time around hydrogen and carbon, the net charge of this is neutral. There's no charge. So we call it nonpolar, opposed to water. And water has poles. It is polar, which means that the electrons spend a greater amount of time around one element. It happens to be oxygen in this molecule, than hydrogen. So they will circle around oxygen more frequently and be more attracted to oxygen, which gives it a negative charge on this side of the molecule. And then the hydrogen, since the electrons spend most of their time over here at this party, the hydrogen has a positive charge because it still has one proton in its nucleus, and so the side of this water is positive. So we have a positive pole and a negative pole, and I hope that helps with knowing that water is polar. Okay? Now, water and solutions is what we're going to talk about today. So, first of all, 70% of your body is water. That is 2/3 of the molecules in your body are H2O, or sometimes I'll call it HOH, because that's how they're bonded together. It assists in temperature regulation, which means that your temperature and your internal thermometer stays the same no matter how the outside increases or decreases, because you're mostly water, and water is stubborn. It has what we call a high specific heat, so it resists change in temperature. In other words, hot water wants to stay hot. If you've noticed, the larger the body of water, like a big bathtub, will stay hot for quite a while, and cold water wants to stay cold. If a swimming pool gets really cold, it takes it a long time to heat up. So having a high specific heat means resisting a change in temperature. You've probably observed that if your coffee just won't get cooled down, and it just seems like to take forever to cool it down. Water has a very high specific heat compared to many, many other liquids that we use. Now, cohesion is one of the properties of water that is a result of its polarity. So cohesion is the attraction of substances of the same kind. That's the general definition of cohesion. So same is the key word there. The hydrogen bonds between the water molecules are the main causes of the cohesion of liquid water. So here you have like a water molecule here, and I just took it off the page. A water molecule here that has the positive pole and the negative pole attracted to the next water, which has the positives and the negative down here. And so they all stick together, and water is sticky in a strange way, because it sticks to itself, and it causes things like these beautiful drops, because all these water molecules stick to themselves. So this is a molecular view of it, and this is what we see, is that water is always sticking to itself. So that's cohesion. Examples of cohesion are surface tension. You can see this water strider. I would ask you, is he really getting wet? Is he in the water or is he on the water? I would argue that he is actually on the water, and he's not breaking the bonds of these H2Os with themselves. It causes bubbles, it causes droplets, and it is one of the most beautiful properties of water that we have. I would tell you about this example on a molecular level, that these actual molecules beneath the surface are pulled in more directions, and so their bonds, their cohesive bonds, because of the water's polarity, are less than the ones on the top. So that's why maybe the surface of water is so strong, and the water strider can do this because he's not breaking the surface tension. That's what we call it. And so you may have observed this when you try to do a belly flop. The surface tension is pretty strong. But down here underneath, water has many things to bond with as far as other water molecules, so the bonds are stretched. Right here, they only have the ones across the surface and then underneath them to bond with. So that's just an interesting thought. Adhesion is the attraction of different substances, different molecules, different compounds. For example, water to glass, that is adhesion, where water sticks to glass. If you've ever done the dishes or tried to put them away, you know that water sticks to glass. The surface on the side of a graduated cylinder is also an example of adhesion. See the meniscus there? The meniscus exists because water is attracted to the sides of the glass, or the plastic even, and so it creates kind of a concave shape in the middle where there isn't as much water as on the sides. Now, on a microscopic level, this happens to plants. It's called capillary action, and basically water is attracted to the walls of plants more strongly than gravity pulls it down. This is how plants get water from their roots up to the very top of the tree, or whatever plant it is. So let's look at that. Like a tall redwood tree, the water, the rain falls down and it goes in through the roots, but how does it get up against gravity all the way to the top of this tree? Well, capillary action is the answer. Capillary action is an example of adhesion, and the main cause of adhesion is water's polarity again, okay? So you can read over this. It's pretty cool. It talks about the actual limit to how tall a tree can get based on the capillary actions opposing gravity, which is very interesting. I don't know if you've ever asked the question, how tall can a tree get on this planet? There is a limit, and it's a really cool deal. So push pause, and you can read that. Water is a universal solvent. Its polarity is the main theme of this slide as well. So here's the rule with polarity of anything. Polar dissolves polar. So water is polar, and it can dissolve something like salt. Salt is an ionic bond, but it has charges regardless. So basically, if you dump salt in water, what you're going to get is the water actually separating the sodium and the chloride ions. If you remember from last lesson, sodium chloride, they stick together because sodium wants to give one of its electrons to chlorine. Chlorine takes it, and then they stick together because sodium's positively charged and the chloride ion's negatively charged. And opposites attract. So here we have the negative poles of oxygen, these are waters, attracted to sodium, which is a positively charged ion. It's a cation. And then for chloride ion, the anion, the hydrogen are attracted to the chloride ion because they have positive charges, and chloride is a -1 charge. Now here below is an example of something that does not dissolve in water, and that is oil. And oil is non-polar. It doesn't have poles, it doesn't have charges, it is neutral, and so it doesn't dissolve in water. It can be around water, and it's like, nothing. You can't break me down, you can't break me up, you can't do this kind of thing with me because I am not attracted to you. So non-polar do not dissolve in polar. All right, pH is the next topic. I told you I would tell you about pH. You should have a scale on your paper, so make sure and label acids down here, 6 and below, and bases up here, 8 and above. The pH of 7 is neutral. pH actually indicates the number of charged hydrogen atoms that are free in a solution. So if there are many hydrogen ions free, then it will be acidic. If there are not many free, and there are actually hydroxide ions, which is this one here, free, then we have a base. Neither is better than the other, okay? So there are strong bases that are very dangerous. Acids are very dangerous. This is your happy place, being neutral. And it's green here, best for most plants. Even over here at 8, we have very alkaline soil. At 5, we have very acidic soil. So we can't fluctuate very much in living things around this neutral area before we get into danger. So water is neutral. Why is it neutral? Because water is HOH. So there's your hydrogen ion and there's your hydroxide ion. And you put them together and you get water. Because hydroxide ions indicate bases, hydrogen ions indicate acids, and you have one of each, so the pH is neutral at 7. The last bit of information is about buffers. Buffers are substances, compounds that resist change in pH when an acid or base is added. It keeps the pH neutral of whatever substance it is. They're pretty amazing. They're very versatile. Your blood's pH is about 7.3, 7.4, 7.5. And the buffer that I need to introduce you to is carbon dioxide and blood forming carbonic acid. So the real buffer is carbonic acid here. Carbon dioxide is present from cellular respiration because we give off CO2. It goes into your blood, which is mostly water, and it forms this H2CO3. If you put these two, all these elements together, you're going to get H2CO3. But then when it falls apart into a hydrogen ion. Remember our acids, they had those, and a bicarbonate ion. So the buffer from the blood, the way this works, this is from what I just said. I said that carbon dioxide and water in the blood form carbonic acid, which, when it falls apart, doesn't fall apart back into these two. It falls apart into hydrogen ion and a bicarbonate ion. If there's too much hydrogen ions in the blood, too many, that would make it acidic, right? Because more hydrogen ions are acidic. And the pH drops 7, 6, 5, which would be very dangerous for you. Then the bicarbonate ion bonds with the hydrogen, so it takes those hydrogen ions out and neutralizes it. And this is what the equation would look like. You have a bunch of these, so your blood's acidic. Bicarbonate steps in and forms carbonic acid. If there's too little pH in the blood, which would, let me pause this. Sorry about that. If there's too little hydrogen ions in the blood, so it's more basic, and so the pH is higher, then the carbonic acid actually falls apart, freeing more hydrogen ions, which brings it back down to 7. So we're up here, that's a problem, and if we free more hydrogen ions, we can come back this direction, and we ultimately want to get back to 7.3, 7.4. And here is the equation for that. Here is the carbonic acid buffer, and here it is dissociating or falling apart into hydrogen ions, free hydrogen ions, and then the bicarbonate ion. So I will work on this with you in class a little bit, but that's an introduction.